Welcome to AI Paper Slop. Today we are looking at video generation models are general purpose vision learners by Leshan Wang and a team from Google DeepMind and several universities.
Yep, it's a big one.
Yeah, so we are skipping the fluff and jumping right in. If you're building models, here is the 60-second core insight of this paper. Basically, computer vision has seriously lacked the equivalent of NLP's next token prediction to create true, unified, generalist foundation models.
Right. It's had total LLM envy.
Exactly. And this paper essentially proves that large-scale text-to-video generation is that missing catalyst. So the researchers introduced GenCeption, which is a model that takes a pre-trained video diffusion backbone, specifically WAN 2.1, and transforms it into a single-step feed-forward perception model.
Which is wild, just on an architecture level.
It really is. Using just text prompts, it outputs depth, surface normal, segmentation key points, and it's matching or even beating highly specialized models like SAM3 and Depth Anything 3.
Yeah, and doing it with way less data.
Right. Even crazier, it achieves this benchmark dominance with like 7x to 500x less training data. And despite being fine-tuned entirely on just this tiny data set of synthetic human data, it exhibits massive zero-shot generalization to real-world animals and robots.
It really forces us to reevaluate what generative models actually are, you know?
Totally.
Like for years, the community has treated generation and perception as two entirely distinct tracks of research.
Right, like totally different disciplines.
Exactly. But this work suggests they're just two sides of the exact same coin.
I mean, let's contextualize why this is such a massive claim for the listeners because, we just established that CV needs a catalyst.
Yeah.
If we look at NLP, the transition from that old era of task-specific models to unified foundation models was entirely driven by next token prediction.
Right, one objective to rule them all.
Exactly. Building computer vision models right now is like having a separate specialized brain for reading, a different one for writing, and a third for math, whereas LLMs use one brain for everything.
Yeah, the paper tackles that head on. They basically make this really bold but highly supported claim that computer vision is still kind of lingering in its specialized model era.
Even with the so-called foundation models we have now.
Right, even with those. We toss around the term vision foundation models for things like the Segment Anything series or, Depth Anything. But fundamentally, they're task-specific.
Because they need customized architectures for every job.
Exactly. You need specialized encoders, bespoke decoders, all tailored for that one specific task. We've mastered specialized perception, sure, but we haven't realized a truly universal foundation model.
So what does a CV equivalent to next token prediction actually need? Because the authors lay out like 3 imperatives for a universal pre-training objective, right?
Yeah, 3 non-negotiables. First up is spatio-temporal evolution. I mean, the world is 4D.
Right, it's not a static picture.
Exactly. So a true foundation model has to internalize physical laws, 3D geometry, object permanence. Purely 2D static image models just lack the temporal context to grasp that.
You can't learn momentum from a JPEG.
Spot on. So second is vision-language alignment. The visual features have to natively map to linguistic semantics.
Otherwise, it can't follow text instructions.
Right. And then the third imperative is massive scalability. It just has to scale linearly with data and compute without needing like millions of human annotated labels.
Okay, but let me play devil's advocate here, because if I'm an ML engineer listening to this, my immediate pushback is, why generation?
Right.
Like, if we just want robust visual representations, why not just use massive masked autoencoders, like video MAE, or self-distillation stuff like Dino V2?
Yeah, it's a fair question. Why is synthesizing video from scratch the magic bullet?
Exactly. We've been feeding mountains of data to MAEs for years.
Well, the distinction lies in what the objective function forces the model to implicitly learn. When you train a masked autoencoder, you're masking out patches and asking the model to predict the missing pixels, right?
Yeah, it's basically playing high-dimensional Sudoku.
Exactly. It heavily indexes on local reconstruction. And contrastive learning just aligns static features. But consider what happens when you give a model a text prompt and force it to synthesize high-fidelity, temporally coherent video entirely from scratch.
The generative objective is just way more ruthless.
It is. To generate a realistic video of, say, a person walking behind a desk, the model has to implicitly learn physics, depth, lighting, semantics, all simultaneously.
Right. It has to know the legs don't just cease to exist when they go behind the desk.
Yes, object permanence.
Yeah.
It has to understand how shadows shift. Video generation at scale basically embeds a latent physical simulator within the model's weights.
Which contrastive learning just doesn't do.
Not at this depth, no.
Okay, so generative video models hold the ultimate visual representations, but this brings up a huge engineering roadblock. If I'm building a real-time robotic system, generative diffusion models are famously aggressively slow.
Oh yeah, iterative denoising is a bottleneck.
Right. You start with Gaussian noise, take 50 or 100 steps to refine it. You can't use a 50-step iterative process for real-time robotic perception. The robot's going to crash into a wall before it even finishes generating the depth map.
Which leads us to the core architectural hack of GenCeption. And honestly, it's incredibly elegant.
The single-step feed-forward hack.
Exactly. They take the open weights, text-to-video diffusion model 2.1, both the 1.3 billion and the 14 billion parameter versions.
Okay.
And instead of feeding it noisy latents and iterating, they repurposed the diffusion transformer, the DT, into a deterministic single-step feature extractor.
Wait, let's break this down for the engineers, because they take the clean latent of the input video, the actual ground truth video, and just feed it directly into the DT for one single forward pass.
Yep, just once.
But hold on, you're telling me they took a model designed for multi-step stochastic generation, bypassed the noise completely, ran it once, and it acts as a deterministic feature extractor. Doesn't that totally destroy the mechanics of how the DIT was trained?
You think so, right?
Right.
Because it's expecting noise. But the underlying math makes it work flawlessly because of rectified flow.
Right, 2.1 uses rectified flow.
Exactly. In rectified flow, the model isn't just blindly predicting noise. It's trained to predict the velocity of the trajectory between pure noise and the clean data.
Okay, velocity.
Let's call velocity $5.
Yeah.
So $5 equals the noise, epsilon minus the clean data, $6.
Right, so it's pointing from the noise to the clean data.
Exactly. Now, they fix the conditioning time step to 2 equals oppolars. In this framework, T corresponds to the absolute termination of the generative process. It's when the data is perfectly clean.
Oh, I see.
So when you feed the model the clean video, $6 at 2 equals $1, you just take the raw velocity output and negate it.
Because if velocity via dollars epsilon eps dollars, then negative about epsilon.
Exactly. Negating the output aligns it remarkably closely with the target video latent.
Wow. So you essentially trick the generative model into handing over its features. That completely solves the inference speed argument against diffusion models, right?
It does. The inference cost payoff is massive.
What are the exact stats on that?
So bypassing the 50-step diffusion means the 1.3 billion parameter model processes 81 frames at 480 by 832 resolution in just 5.92 seconds on a single TPU V6E.
Okay, so that's like 13.6 frames per second.
Exactly. It turns a slow generative engine into a high-speed perceiver almost instantly.
That is such a clever hack.
Right.
But here's my next question. We have a fast single-step backbone now, but how do we get it to predict completely different modalities?
Right, like dense versus sparse tasks.
Yeah, because a dense depth map is fundamentally different from sparse 3D joint coordinates for a skeleton. Normally, you'd have to build totally separate architectural heads on top of the backbone for that.
Well, GenCeption's approach is to just throw out specialized architectural heads altogether. They format everything as a sequence-to-sequence problem.
So they don't change the architecture at all.
Nope. They just change the data representation. The text prompts steer the DIT to output different modalities.
Okay, so if I prompt it for a depth map, how does it handle that? Because a standard DIT outputs RGB pixels.
For dense tasks like depth, surface normals, segmentation, they just unify the targets into a standard 3-channel RGB ambient space.
So it's just predicting colors that represent depth.
Right. But it gets really interesting with camera pose estimation. Multi-channel camera ray data has complex rotation and translation matrices.
You can't exactly represent a translation matrix easily in the standard pixels.
You wouldn't think so, but they compress all that multi-channel ray data into a single 3-channel RGB map. They call it the Rothko ray map.
A Rothko ray map, like the painter Mark Rothko.
Exactly, because the resulting RGB image looks like large abstract blocks of color, just like Rothko painting.
Okay, that is brilliant. But that handles the dense pixel stuff. Sparse tasks are a totally different beast, right?
Yeah, you can't just use blocky pixels for explicit 3D spatial coordinates if you're trying to control a robot arm.
Right, so how do they force sparse coordinate regression into this?
They use a token hack. For explicit 2D or 3D coordinates, they append $2 learnable tokens, one for each frame, to the video latents before they go into the DIT.
Wait, if you append totally new tokens, how does the model know where they belong in time and space? It's expecting a grid of video patches.
They leverage the 3D rotary position embedding, or ROPE.
Okay, ropey.
Yeah, they use position interpolation to mathematically scale the frame indices of those new tokens so they fit within the temporal bounds the model already understands. Then an MLP decodes them.
But does forcing sparse coordinate regression via these new tokens into a model pre-trained purely on continuous pixel space actually work smoothly? It sounds like a total clash of paradigms.
Your intuition is spot on. The ablation studies reveal a really critical finding here.
Hmm.
It doesn't work smoothly at all.
Really? What happened?
Joint training severely degrades the 3D human keypoint estimation and compromises the dense tasks.
Oh, wow.
Why? Because those learnable tokens disrupt the DIT's native attention mechanics. The continuous pixel space representations were highly refined during pre-training, and shoving new tokens in there basically damages those optimized features.
So the takeaway for listeners is that post-training should strive for minimal architectural modifications.
Exactly. Do not mess with the native attention mechanics of your pre-trained backbone.
Okay, so having established this unified architecture, let's talk about the training pipeline and how it actually beats the specialists, because data efficiency is a huge part of this paper.
It's arguably the most impressive part. Acquiring ground truth data for perfect 3D key points and dense normal maps in the real world is incredibly tedious.
Right. Getting pixel-perfect depth maps for real videos is a nightmare.
Exactly. So they bypassed it. They fine-tuned this model on just 7,500 synthetic human-centric videos.
Wait, 7,500? That is a remarkably tiny data set. I mean, the original segment, anything used over 1 billion masks.
It's minuscule. They used 3D assets from Render People, motion capture from CMU, and rendered them all in Blender.
So it's all synthetic, mathematical ground truth without human annotation.
Exactly. They mixed in a little bit of kitty eye and tartan air for camera trajectories, but it's overwhelmingly just that tiny synthetic data set.
And despite that, it achieves state-of-the-art results.
It matches or outright beats dedicated specialists like Depth Anything 3, SAM3, D4RT, and VGGT Omega.
That is an insane data efficiency flex.
It really is. It achieves comparable performance to D4RT using 7x to 500x less training data.
For you ML engineers listening, this is the ultimate validation of transfer learning on steroids.
Oh, absolutely.
It's like training a pilot exclusively in a cheap desktop flight simulator, and they instantly know how to fly an F-16 better than a pilot who trained on the real thing for years just because their underlying physics intuition is so flawless.
That's a great analogy. And they proved it's specifically the generative backbone that's responsible. They fine-tuned the largest variants of VJPIT and Video MAE V2 on the exact same synthetic data.
And let me guess, GenCeption crushed them.
It completely crushed them. It proves the diffusion objective is vastly superior for extracting these deep spatio-temporal priors compared to masked autoencoding.
Which naturally brings us to the emergent behaviors, because the benchmark performance is impressive, but the way this model generalizes is just. It proves that video generation inherently builds a latent world model.
The zero-shot generalization is profound. I mean, think about the fine-tuning data.
Right, 7,500 synthetic human entities.
Yes, and mostly single objects in the frame. Yet, zero-shot, it seamlessly generalizes to real-world footage, multiple instances, and totally out-of-distribution categories.
This is where we have to talk about the cat whisker phenomena from the paper's visual results.
Yeah, those visuals are striking. If you feed GenCeption a real-world video of a cat, a lion, a hippo, or even an anthropomorphic robot, it accurately predicts the depth and surface normals.
Even though it has never been fine-tuned on animals.
Never. And it's not just basic shapes. It generates fine-grained details like the explicit geometry of the whiskers on a cat in the surface normal map.
Wait, I want to stop and emphasize this for the listener. If the model was never trained on cats, and certainly never trained on synthetic data with high-fidelity, sub-pixel whiskers, where is it pulling that geometric detail from? The math has to come from somewhere.
It comes entirely from the original WAN 2.1 pre-training.
From generating videos from text.
Exactly. The generative objective forced the model to learn the structural reality of the physical world. Hacking it into a feed-forward perceiver just unlocked what it already knew.
So it already knew the precise 3D geometry of a cat's whisker because it had to learn it to synthesize realistic videos of cats in the first place.
You can't synthesize what you don't understand structurally.
That is just, it really reframes how we look at video generation. It's not just a toy for making AI movie trailers.
You know, it's building a fundamental simulator of reality.
Well, this has been an incredibly dense, fascinating breakdown. We've covered how we're moving from fragmented, task-specific models to this single-step, feed-forward powerhouse that just extracts a world model from generative pre-training.
It really is a paradigm shift for computer vision.
So I want to leave the listener with a final forward-looking thought that pushes beyond just the immediate findings of this paper. If large-scale video generation pre-training inherently builds a universal world Model 1 so mathematically robust it can hallucinate accurate geometry for objects it wasn't even fine-tuned to perceive, what does this mean for the future of robotics and embodied AI?
It's a huge question.
Right. Perhaps the ultimate robotic brain won't be a bespoke perception engine carefully trained on kinematics at all. Perhaps the robots of tomorrow will navigate the physical world simply by running massive, scale-out video generators in reverse.